Imagine you walk into a library where there is none of the books in order. Every time you want to find something, you have to walk through every aisle, read every spine, which probably is going to take forever, right? But if the books are alphabetically sorted by author, suddenly everything becomes a little bit more effortless, let's say. That's exactly what sorting does for computers. Hello everyone, and welcome to one more episode of the Tech Odyssey podcast. I am your host, Mike, and here in Tech Odyssey, we break down technical concepts in a way that is clear, it's practical, and it's easy to understand. Regardless if you are entirely new in tech or if you're a couple of years in, this podcast can be your guide to get insights from the real world and understand how tech really works behind the scenes. In today's episode, we're diving into something that sounds simple, but hides a world of clever ideas underneath, sorting algorithms. Now, I know that this might sound a little bit abstract, but stick with me. Because sorting is one of those things that computers do constantly. Every time that your playlist is organized alphabetically, or every time that you search for the highest score somewhere, or even when your email inbox puts the newest message in the top, a sorting algorithm is quietly doing the work in the background. So today, I want to take you on a little journey. We'll explore how computers organize chaos, how they take a messy pile of data and put it in perfect order. And I'll try to describe it in the way that you can actually imagine. Not many visuals, no code, just stories. Before we get into how, let's start with why sorting matters. Imagine you walk into a library where there is none of the books in order. Every time you want to find something, you have to walk through every aisle, read every spine, which probably is going to take forever, right? But if the books are alphabetically sorted by author, suddenly everything becomes a little bit more effortless, let's say. That's exactly what sorting does for computers. A sorted list means faster searches, cleaner organization, and less chaos. So now that we know why sorting is actually important, let's meet the stars of today's story. The algorithms themselves, basically. Each one has a different personality, a different style of solving the same problem, let's say. So let's start with a simple one, the bubble sort. Picture this. You have a line of people standing by height, all mixed up. Now, the shorter person looks at the taller one next to them, and if they are out of order, they swap. Then the next pair does the same, and again and again. It's like little bubbles rising to the top. That's why it's also called the bubble sort, basically. It's simple to understand and easy to follow, but there is a catch. It's super slow. It keeps checking and swapping again and again and again, even when most of the list is already sorted. If bubble sort was a person, it would be the friend who is trying to refold everything in the laundry 3 times just to make sure that everything is perfect. Lovable, but not the fastest. Let's go to the next algorithm, the insertion sort. Now imagine that you're holding a handful of cards. Okay? You start by one card. That's already sorted. Then you pick another card and insert it into the correct position. You keep doing this card by card until your whole hand is in perfect order. That's the insertion sort. It's neat, it's intuitive, and it works really well for small amounts of data. It's what humans actually do. We take one item, put it where it belongs, and leave it there. No drama, no complexity. But if the list gets too long, say 1,000 of items, it starts to slow down too. Still, it's great for simple everyday sorting when the items are not too many. Next up on the list is the selection sort. In selection sort, it doesn't bother with constant swapping like the bubble sort. Instead, it scans through the entire list and finds the smallest item and moves it to the front. Then it repeats the same for the rest of the list, one step at a time, until everything is in perfect place. It's like saying, let's not touch anything until we find exactly where it belongs. It's calm, it's deliberate, and it's predictable. But again, not the fastest, especially for large amounts of data. Still, it's easy to understand, and that's why many programmers learn it early on. Now, let's go to the next one on the list, the QuickSort. Now, this is where things start to get interesting. The QuickSort is where cleverness enters the room, basically. It doesn't look at the entire pile, it divides and conquers. Here is how it thinks. Pick one random item, that's your pivot. Then split everything into two groups where every smaller than the pivot goes to the left and everything larger than the pivot goes to the right. Then you repeat that process for each group over and over again until everything is sorted. It's like organizing your books by genre and then alphabetically within each genre. And you break down the problem into smaller pieces until sorting feels effortless. So QuickSort is fast. It's very fast, basically. And that's why it's used in many modern systems. It's the strategist of the group, let's say. It's efficient, it's sharp, and it's clever. And then we have the Merge Sort. Imagine splitting your messy pile of papers into smaller and smaller stacks until each stack is just one paper. Then you start merging them back together, always merging two stacks at a time and making sure that the merged stack is in order. By the time you're done, you have one perfectly sorted pile. Merge Sort is beautiful because it's organized, it's predictable, and it works great even with massive amounts of data. It's like teamwork. Lots of small helpers working in parallel, combining their effort to achieve something big. This one is often used in big systems where efficiency really matters, like databases, distributed systems, you name it. The downside of this is that it requires a lot of memory. And then you have the heap sort, which is something like a priority manager. Imagine you have a pile of rocks at different sizes. Instead of sorting them one by one, you build a special structure, a heap. It's a kind of organized pile where the biggest rock always rises to the top. Here's how it works. You build this heap structure from your list. The largest item automatically bubbles to the top. You remove it and place it in the end of your sorted list. The heap restructures itself and you repeat until everything is sorted. It's like having a magical assistant who always hands the biggest remaining rock without you even asking. Heap sort is efficient, it's predictable, and it has a guaranteed linear arithmetic performance every single time. It's not the fastest in practice, but it's extremely reliable, which is why it's used inside many system-level tools and libraries. It's the sort of algorithm that quietly does its job without showing up. Alright, now that we've walked through each algorithm individually, let's wrap things up by organizing them side by side, because this is where all the big O theory suddenly starts to make sense. First, let's start with the winners, the algorithms that scale even when the dataset explodes. The most reliable one is Merge Sort. Merge Sort gives you linear arithmetic time performance every single time. No surprises. If you want predictable speed and you are working with really large datasets, this is the safest option. And then we have QuickSort. QuickSort is usually the fastest in real-world scenarios, and it also averages linear arithmetic time performance, but it can also hit quadratic performance sometimes in the worst-case scenario. Modern implementations mostly avoid that, but the risk is still there. And then we have heap sort, which is also a guaranteed performer. Has also linear arithmetic time performance in every scenario, no surprises. It's not as fast as QuickSort in practice, but it's extremely predictable. Then let's move to the simpler algorithms, the ones that are easy to understand but don't scale as well. Next one on the list is the insertion sort. It's surprisingly good for tiny or almost sorted lists. It has quadratic performance in general case, but almost linear time performance when the data is already short. Then we have selection sort, which is consistent but slow. It has quadratic performance no matter what, and the only advantage really is that it has fewer swaps. It's great for teaching, but not for performance. And in the bottom tier, we have the bubble sort, which is the slowest of all. Bubble sort does a lot of unnecessary work. It's intuitive, it's visual, but it's by far the slowest way to sort anything. So finally, putting it all together, the ordering looks like this. First of all, we have the Merge Sort, which is the best worst-case performance. Second, we have the QuickSort, which is usually the fastest in practice, but there is a little bit of risk sometimes. Then we have the Heap Sort, which is also a guaranteed performance. Insertion Sort, which is good for small or nearly sorted data. And finally, we have Selection Sort, which is simple, predictable, but slow. And the worst of all, which is Bubble Sort, which is the slowest, and it's only for education purposes. So when to use what? Merge Sort when you want reliability, QuickSort when you want raw speed, Heap Sort when the worst case scenario matters, Insertion Sort when your data is small or nearly sorted, Selection Sort when you want simplicity, and Bubble Sort when you're teaching, not building. So what can we take out of all of this? Sorting algorithms aren't just about numbers and code. They are about approaches to problem solving. behind every fast search, every ordered list, and every efficient system, there is a sorting algorithm quietly putting things in place. So next time your computer sorts something instantly, remember it's not magic. It's math, logic, and a little bit of art. If you enjoyed today's journey into the world of sorting algorithms, consider following the show. And also, if you like, share it with a friend who loves learning how tech really works behind the scenes. Until next time, stay curious, keep exploring, and remember, every bit of order starts from a little bit of chaos. Thanks for joining me to another episode of the Tech Odyssey podcast. I'm Mike, and I will see you in the next one where we will keep exploring the world of tech one step at a time.